If you recall, we already studied the relative motion of two particles. However, our previous study was limited to translating frames of reference. In other words, the motion of the moving coordinate system is only translating with no rotation. If you also recall, in this example, Ra and Rb are both absolute positions with respect to the fixed reference frame, and the relative position vector of the two particles is simply the difference of the two absolute position vectors. This is still true even when the moving reference frame is rotating, as we will discuss in this video. You probably also remember this. If we take the time derivative of the relative position equation, we get the equation for relative velocity. And if we take the time derivative again, we get the equation for relative acceleration. However, let me remind you, for translating frames, the unit vectors I, j, and k do not change with time. So from here to here, there is no need to apply chain rule since only the x, y, and z positions are functions of time. As you can tell, this is going to change for rotating frame of reference. So now let's revisit this scenario, and for simplicity, let's focus on a 2D plane only. This time, the moving coordinate system, represented by the small case letters x and y, is rotating with angular velocity omega and angular acceleration omega dot with respect to the fixed frame. Notice that the moving frame could be translating at the same time as well. The origin of this frame is at point A and is moving with point A. Ra and Rb are still the absolute position vectors of points A and B measured from the fixed frame, and the difference is still the relative position vector, in this case B relative to A. This relative position vector can be represented in either the fixed frame or the rotating frame. Now, to get the relative velocity equation, again, let's take the time derivative of this relative position equation. Don't forget the right-hand side is the difference of the two absolute position vectors. Therefore, after we take the time derivative, the right-hand side is now the difference of the absolute velocities Vb and Va. Let's focus on the left-hand side. Again, the relative position vector is represented in the xy frame, the rotating frame. But don't forget, the unit vectors I and j are variables now, because even though their magnitudes will remain a constant one, they do change directions with respect to time. Therefore, when we take the time derivative of this relative position vector, we must now apply chain rule. This part right here looks familiar to us, and it is the velocity of point B observed at point A in the xy rotating frame. In other words, the relative velocity of point B as measured by point A. But what about this part? You probably have seen similar approaches before. Let's say this is the rotating frame with angular velocity omega. Don't forget, this omega is a vector with unit vector k that is perpendicular to this xy plane. After some time dt, this is its current orientation. This is the change in unit vector I di. Its magnitude can be approximated as the length of an arc with a central angle d theta, and its direction is represented by unit vector j from observation. Therefore, di dt equals to d theta dtj, and because d theta dt is the magnitude of angular velocity omega, this term becomes the cross product of vectors omega and I if you are familiar with the cross product rule. And we can derive dj dt in a similar way. Plug them back. Recognize that xi plus yj is the relative position vector Rb relative to A. Therefore, we get to this equation that relates the absolute velocities of points A and B. I will explain more the meaning of each term in an example later. And similarly, from here we can take the time derivative of this entire equation in order to get the equation that relates the absolute accelerations of points A and B. Notice that we applied chain rule here again. And remember, we derived this equation earlier. So very similarly, we can derive this equation. And therefore, this is what we get, which can be simplified slightly. Omega dot is the angular acceleration of the rotating reference frame. And this term right here is the relative acceleration of point B as measured from point A attached to the rotating reference frame. Now let's look at examples. Let's look at this example. There's a horizontal surface that is rotating about point A with angular velocity and angular acceleration as shown. There's also a toy duck that is moving along a straight line on this surface, and its relative linear velocity and linear acceleration on this line are also given. We need to determine its absolute velocity and acceleration at this instant. First, we want to set up our coordinate systems, a fixed reference frame represented by capital letters X and Y, and a rotating frame represented by small case letters XY, which is currently superimposing with the fixed frame at this moment. The difference is the rotating frame is fixed at the rotating surface, therefore it has the same angular velocity and acceleration of the surface. You can imagine a moment later, the rotating frame will no longer be superimposing with the fixed frame. Since this problem is very straightforward, we are asked to determine the absolute velocity of the duck. We will use this equation directly. In this equation, VB is the absolute velocity of the duck. VA is the absolute linear velocity of point A. In this case, it's 0 because it's the center of rotation. Omega is the angular velocity of this rotating frame, 0.4 k. RB/A is the relative position of B with respect to A. In this case, this vector here, 1I. And this last term is the relative linear velocity of the duck, 0.2I. Therefore, with all the information, we can determine the absolute velocity of the duck. Notice here I represent all the vectors in the rotating frame with small case letters. As a general rule, you can also represent all vectors in the fixed frame even if the two frames do not coincide. Your final answers may look different, but will have the same physical meanings. Now, let's take a further look of this equation and see what it means. Since you have already studied the rigid body general plane motion with relative motion analysis, this part should look very familiar to you. If you consider the rotating frame as a rigid body, then you will recognize that this is the absolute linear velocity of point B that belongs to the XY frame. This velocity is the result of the rotation of the frame. But don't forget, the duck still has a relative velocity with respect to this point B. Therefore, combining both of these two contributions, we get the absolute velocity of the duck. To determine the absolute acceleration of the duck, again, let's first use this equation directly for calculation, because this is the absolute acceleration of the duck, and then we will explain later. The linear absolute velocity of point A is again 0 because point A is the center of rotation. This is the angular acceleration of the rotating frame, 0.1 k. This again is the relative position of the duck with respect to point A. Magnitude of the angular velocity vector, relative velocity of the duck, and relative acceleration of the duck. With all this information, we can determine the absolute acceleration of the duck. So again, based on your previous knowledge of the relative motion analysis, you would recognize that this part right here is the absolute acceleration of point B that is on the rotating frame. And on top of that, the duck also has a relative acceleration with respect to this point. This term right here is new. It's called the Coriolis acceleration. You are encouraged to learn more about it on your own. But for the purpose of this course, just consider it as an important mathematical correction factor that must be included when using the rotating reference frame. When combining all these three contributions, we get the absolute acceleration of the duck. Let's look at this example, which should look very familiar to you. Object A is traveling along the circular path and object B is traveling along a straight path. The information on their respective absolute velocities and acceleration is given, but this time we need to determine the relative velocity and acceleration of object B with respect to A. Since object A is traveling along the circular path, in this example, we are going to observe the motion of object B in a rotating reference frame. So first, we set up our coordinate systems. Currently, the fixed reference frame represented by the capital letters and the rotating reference frame represented by the small case letters coincide, and they are both set on object A because object A is the observer. But the difference is the rotating reference frame will move together with object A along this circular path. And from the absolute linear velocity of object A as well as its absolute linear acceleration, we can determine the angular velocity of this reference frame as well as the angular acceleration. And now we're going to use this equation again, but the difference is now we do know the absolute velocity of object B as well as the absolute velocity of object A. We just determined the angular velocity of this rotating reference frame, and this is the relative position vector of B relative to A. Notice that all vectors are represented using the rotating reference frame. And now in this equation, the only unknown is the relative velocity of B with respect to A, and from here we can solve for it. And if you remember from before, this is the relative velocity of object A with respect to B, and you can see how different they are. Similarly, for the relative acceleration of object B, we are going to use this equation. We do know the absolute acceleration of object B, as well as that of object A. Don't forget, this acceleration has both normal and tangential components. We also know the angular acceleration of this rotating frame. This is the same relative position vector. This is, again, the angular velocity of this rotating frame. This is the relative velocity of object B with respect to A that we just determined. Therefore, in this equation, the only unknown is the relative acceleration of B with respect to A. And from here, we can solve for it. Again, please notice how this is different from the relative acceleration of A with respect to B.